Okay, remember, right now we're fighting with the key agreement um, of the verification material agreement. Um, so we want to understand, so we want to understand what is this verification method? Material agreement type. All right, so it's one of these JSON Web Key 20. All right, so we're going to just try all these, see what one works. Cannot concatenate. Verification type agreement. Verification method type. Verification method type agreement. And then so what, I give you a JWK. Did you have two different values before? Let's see. Yeah, so these were two different values before. Encryption keys, signing keys. Okay. We are what, decode? Now, oh, what's this? Assumptions and limitations. Only, okay, so only ED25519 keys are supported for authentication, and only X25519 are supported for agreement. Okay. Supported verification materials. Input in. Default verification materials. ED verification. And X key agreement key with multi-base 58. Base 58. Public key, multi-base public key encoding. JWK JSON Web Key. Input and in the result. So JSON Web public base 58. So verification key only X. Okay. So what is this? Do we need a different type of key? Okay, so only these X whatever keys are supported for key agreement. So what is this? User scribe, okay. Okay, so X25519 is when we're doing Diffley Hellman operation, and ED25519 is for EDDSA signature. Okay, so okay, yes, and I'm told that this stuff will have to change apparently, which we will need to be talking to probably Daniel or somebody about, because this is apparently this needs to change. From what I'm hearing. Okay, so X255. All right, this is not jumping out. All right, if we use a secret scalar, 2 points that are published, so we can convert the one there with the maps above. Notice that, well, both an X and Y. You couldn't, that's because you couldn't aren't enough to do that. So that's because you, for every valid U coordinate, there are 2 points on the McGovern curve. This is the same. This is the same as true of Y coordinates in the Euclid's curve. That's why we can encode in the Y sign bit. This looks like some hacky ass shit. This is sketch. Okay, never mind. All right, he knows what he's doing. I thought this guy's name looked familiar. Okay, fantastic. Um, all right. Professionalize the role of supply chain security. All right, well, let us keep this for our research as well because I am wholeheartedly in support of what I believe this guy is saying. But we need to figure out. I think we should definitely ensure that people are paying open source maintainers. Let's see. Remains cross is checking for cross protocol attacks. Partial decryption oracle generated can be used into. Okay. Okay. Let's see. Okay, so Libsodium has routines to do this. Authentication, encryption, and signatures. Okay. Yeah, so this is actually irrelevant, I'm realizing. So, um, we we don't need to care that we're only using this thing for signing because we can add another key for encryption if we wanted to. We don't need to care about using the key for encryption because we only need it to. Okay, so we do need one key to sign the. Okay, wait a minute. So we do need one key to sign it. Does that require that it gets encrypted? And we can close down this Hyperledger stuff for now. I think we found out it's probably like a for later thing. It definitely seems like an opportunity. Okay. What is this base 58? Okay. Let's just blow this up for a second. I want the view, this view. There we go. Now I can read. All right. Oh, thank you. Oh my God, that's so much better. Okay. Oh my God. Oh wow, look at that. We can actually see. Um, so basically, no DISO is the same as key to both sign and encrypt in crypto. Let's add this link. All right, closing some tabs. This looks pretty great. This thing, this Node.js thing, I just don't want to pull in a dependency on Node.js right now. I mean, it's anybody. Let's see. Okay, yeah. All right, so we may not even need to care about this encryption thing because all we really care about is, doing this, right? This really what amounts to a signing flow. So okay. So basically verification, so encryption keys Create pure DID numalgo2. So let's go read what is this numalgo2. Method 2. Alright, similar to method 0. Is there 1? Genesis doc. Create a Genesis version of a JSON document. Genesis version must define a single key with the register privilege. This inception key should create a doc that is the key that creates the DID and authenticates when exchanging it with the first peer. It should include enough state subsequent evolutions to the doc are authorized. Otherwise, the doc is static, suitable only for layer 2 use. Must not include the DID itself, either the root ID property or its value. This lets the doc be created without knowing the DID's value in advance. Suppressing the DID value creates a stored variant of the pure DID data doc as opposed to a resolved variant that would have an actual DID value in the root ID property. In either stored or resolved variant of the doc anywhere else that the DID value would appear, it should use a relative reference on the absolute value. For example, each controller property of a verification method that is owned by a DID would say controller #ID. Okay, so I think what they're trying to tell us is by hashing the store variant, we avoid the circular problem of including the DID in the data that's being hashed. This means that a pure DID doc must be resolved by converting a stored variant of the DID doc data into a resolved variant by inserting the value of the DID being resolved. By deriving the number basis of the DID from the Genesis version of the DID doc, the DID can begin its lifecycle with any number of keys and endpoints. Using a protective M of n policies, the inception key is the part of the Genesis state that's true bedrock. All other information is optional, can be thought of as a sort of pre-rotation or pre-evolution, initiated by the inception key to a more complex state. The root of trust for pure DIDs is the entropy in the inception key. The inception key must be new for each DID. It must not ever be reused, and it must be the case that anyone observing the public half of the inception key cannot somehow steal the private half. This guarantees that nobody other than the holder of the inception key could have created the Genesis version of the DID doc, because only the inception key has the privilege of sharing the DID doc with a peer. No other key holder can establish a relationship contrary to the intent of the inception key holder. This gives pure DIDs a self-certifying property that is vital to cybersecurity of all its DIDs. Any DID method that does not guarantee the chain of custody of the DID between when it is created and when it is shared, e.g. written to a ledger or given to a peer, lacks this quality and is susceptible to attacks early in the DID's lifecycle. See this GitHub issue for more details. Anyone can ledgerize, all right. Okay, so a discussion thread around the vulnerability has started in the W3C CCG. Here's a quick summary of the background. Smith, Samuel M. and I have been discussing an issue that I wanted to bring to this group. It is a risk that Sam has described as anybody can ledgerize problem. What is to prevent someone other than the owner of the DID from recording the initial version of a DID doc on the ledger, thus making public something that the owner intended to keep off the ledger for the time being or permanently. Even though this question is framed in the terms of ledgers, it has direct application of non-ledger DID methods as well. I believe that some DID methods allow anyone with right permission or willing to pay transaction keys to write a DID in its initial DID doc to the shared source of truth. Since the DID doc just contains public keys, all the other info might be known to someone other than the DID's owner, another party in the list of controllers, for example, even an adversary. Yes, this adversary possesses none of the private keys, so cannot control the DID after registration, but the mere registration of someone else's data could, in effect, constitute mischief. To guard against abuse, the correct behavior of a ledger is probably to require that the request to write the Genesis version of a DID doc be signed by a key in the DID doc, of course, yeah. Note that just signing the DID doc isn't enough, since the attacker could have captured the signature when he captured the DID doc content. Even better security would require the DID value to be derived from a key in the DID doc, and the initial write request use that key as well. Perhaps this protection against abuse needs to be a rubric, or perhaps it is more fundamental and needs to be a requirement of all DID methods, period. Now I'd like to reason about how this applies to pure DIDs. Here's how it could play out. Alice's Agent 1 creates a DID doc for a relationship with Bob, naming keys for Agent 2 and Agent 3 are as also authorized. Then Alice's Agent 2, which may have been hacked without Alice realizing it, oh no, can take that DID doc and send it to Carol using the Agent 2 key to sign. Okay, so Alice's Agent 1 creates a DID doc for a relationship with Bob. Okay. Preserving no. DID doc is authoritative for events after origination, but cannot be authoritative for origination itself. The genesis of the DID doc is too late. It occurs after origination of the public-private key pair. The ledgerization attack is one example of what happens when a root of trust for origination is skipped. One reason for this misconception is that crypto textbooks, indeed much of crypto practice, assume that there is some authority that originates public-private key pairs and therefore or or origination is a given, but this is inherently centralized. In a decentralized system, there is no unique origination authority, so it's a bootstrap problem of self-certifying identifiers, which are not mentioned in most crypto textbook. Elegantly solve the bootstrap origination authority problem by including the public key in the identifier. This means only the creator of the public key is uniquely able to certify as their origination authority via the associated private key, and importantly, an entity may likewise be the only verifiable organization authority for any sufficiently collision-resistant key pair they create. Assuming sufficient entropy, the authority is derived from a vanishingly small probability in any other entity that could create the same public-private key pair. In namespacing identifier, so basically they're saying if you put like the fingerprint in the thing you're going to sign, then obviously, uh, or yeah, if you put the fingerprint in the thing you're going to sign, and I think this is the thing we're going to hit on here too. Okay, that's a lot. Uncontroversial, though we want self-centered discussion. How do we use pre-rotation while still preserving the characteristic that support for key rotation with pure DIDs is optional, layer 3, and without modifying the DID exchange protocol, which allows the DID doc to be exchanged at the inception of a relationship, it does not allow deltas to accompany. If you have ideas about answer to each of these questions, I'd be interested to hear. Exchanging a DID doc at the inception of a pure DID relationship, then the DID doc thus exchanged could include a block that includes the key event receipts upon the creation of the DID doc. Usually this would just be the inception and one rotation of the identifier, but it could include any number of rotations. These rotations are not deltas on the DID doc, but established via verification of the receipts the current authoritative keys for the identifier, but established via verification of the receipts the current authoritative keys for the identifier, and hence the DID doc origination as provided. In other words, the DID doc origination event is not the inception event for the identifier. The DID doc origination event includes the DID doc and the key event history receipts for the rotations. The concept is to decouple or remove the DID doc as the primary source of the key event state, replace it with much more compact key event receipts, and then the DID doc becomes a snapshot of the key event state by including the key event receipt log and signatures of the DID doc with the current authorities keys. For non-pure DIDs, the DID doc would include a designation, the infrastructure that provides the key event state. There's your provenance information. But for the pure DIDs, it needs to be self-contained. In the Curie parlance, the DID doc is an interaction event, not a key event. This approach is generalizable to any protocol and also is used to support the delegated credentials you wonderfully subscribe today. And so this is why, this Web3 stuff is interesting because it's a generic protocol. Because we can use all these keys to create whatever trust relationships we want. Closing this issue because we moved the repo and we're determined to redeem purities. This will naturally cause us to resolve the concern here, therefore. Okay. Tech are reusing a purity in a different context. Curie requires pre-rotation. Quantum security IDs. The Curie principle for DID union method and its associated DID doc is that the control authority over the DID doc must be established as part of any verifier syncing verification. So following Curie, what is this? IETF Curie. Key event receipt infrastructure. What is this? This looks important. Where did it go? Okay. In Curie the DID doc. Okay, so following Curie principles in DID peer should fix the problem. I don't know exactly what yet the fix looks like for DID peer. In Curie, the DID doc is not the root of trust. The curl is. The DID doc may provide a snapshot of curl or a reference to the curl by which the DID doc authenticity may be established. Thus, moving DID peer to a Curie approach changes how one looks at DID peer doc. Oops. Following Curie principles. A snapshot of Carol for reference to Carol. That's what changes how one could use a sequence of DID. Okay. In Curl, the DID doc is not the root of trust. The Curl is. DID doc may provide a snapshot of the Curl or reference to the Curl by which the DID doc authenticity may. Okay. Thus, moving DID peer to a Curl changes how one looks at DID peer doc. One could use a sequence of DID peer docs. DID docs is the equivalent of a Curo, but the control establishment for each new DID doc would have to follow Curo principles. Each version of a DID doc would function either as an establishment event or a non-establishment event in the Curie parlance. These versions that function as establishment events would have to be signed appropriately in order to establish a transfer of control authority rotate keys, so a DID doc could not be used in an inconsistent sequence of events without being detectable. Okay, yeah, I talked to Matt about key revocation stuff earlier today, and this sounds like it's what it's hitting on. Um, so we need to read this thing. What is this? Quantum secure DIDs, perfect. How to design a given DID method post-quantum secure with existing 2020. All right. Making DID methods and quantum. All right, so DID CRUD mechanisms. Using the Ethereum lightweight identity standard ERC 1056, the default unconfigured DID document can be considered quantum secure, but when the DID document is first configured, a blockchain transaction is signed and the public key is revealed. Unless the public key is deactivated by rotation, the DID document cannot be considered post-quantum secure anymore. Normative guidance. Oh, it's because the quantum computers, if they know the public portion, they can break the private portion for some things, especially these shorter byte keys that they use here, like the ED 25519s, and the ED, or what's the other one? The other short one that they use for SSH. This is why I personally prefer the RSA 4096 keys. Let's see. Da, da, da. All right, okay, I'm obviously not reading this. Okay, Curie approach. This uses a pre-rotation scheme for each rotation event that makes a forward cryptographic commitment to the next key rotation. Curie uses a pre-rotation scheme in each rotation event that also makes a forward cryptographic commitment to the next rotation key or set of keys. Pre-rotation is an elegant way of managing rotation keys. With pre-rotation, a given rotation key can only be used once. For this forward commitment, it is expressed as a digest of the next key of the next rotation key set. Then the pre-rotation can be considered post-quantum secure. The latest version of the Curie design white paper proposes this approach. Details of the scheme can be found here. A nearby diagram shows the basic idea of pre-rotation with post-quantum secure. Digest of the next key sets. Okay, well, you had me sold. Once you said each rotation event also makes a forward cryptographic commitment to the each next rotation key or set of keys. So it sounds like basically they're going to change the numbers in the keys to make it a different key. So every time it's almost like you're not going to be able to guess it. It basically it's getting blown up every time it gets used and rotated to the next thing, which you're not going to be able to tell the next thing from knowing blowing up the last thing, sort of. Okay, so this is great work. And it looks like, I mean, as far as we've found, we basically followed Sam here, and the inevitability, God is inevitable. Have an aspiration of God. Hey, given the likelihood that it's inevitability recursion, the human aspiration to godliness is the inevitable result of Godhead. The intent of this post is to define the hypothesis. Life happens. It's got a notable what why not? Wow. This is exactly what I've been thinking. Um, oh, but now this is different. This part I agree with. Uh, to some extent, I think it's interesting. Um, hmm, interesting. Okay. Uh, Web of Trust. 6 days ago, key of sheet infrastructure. All right. Mm, okay, this is just this guy though. That's not good. We can't base the whole world's web of trust off of one guy's project. Although it does look like a very good project. Maybe we should do it. Let's do it. Come on, let's live a little. Project working towards IT. Yeah, I think they're right, quite honestly. I think this is the same thing as like the signal thing. You need to these people know stuff about the quantum computers. Let's see. So, oh, okay, great. No, they have more people. Great. All right, yeah, let's do it. There's more than one person on this project. We're going all in. Okay. They have a read the docs. Where is it? CurryPy. Oh no, the docs are failing. Ledgerless. Perfect. That's what I want to hear. Don't want to have to use a ledger. How do we use it though? Development. Testing. Oh no. Oh, what's this? Hmm, what is this? What is this? Hmm, 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 hmm. Where's Alice? Hmm, I'll have to make one. Hmm, 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 hmm. Hmm. demo. Okay, so when installing Curie with pip, we get these two scripts. So they exchange event messages. Um, hmm, okay. Hmm, hmm, hmm. I'm going to bed.